start the recording here. Today we have the pleasure of hosting Tali Beynon, formerly of House Wolfram and now an independent researcher conducting his studies at the intersection of geometry and computation. Tali reached out to me a few years ago to discuss our shared interest in computation graphs, and I'm so glad he did. He's a man of few words, but if you listen carefully, they're full of musical, practical, and at times profound ideas. One of the things I admire most about Tali's work is that it reframes abstract geometric concepts in terms that a layperson might understand. I don't understand all the words right away, but I can tell you I hear the song of our people. On the few occasions we've met, Tali has shown me the value of these abstractions in a language that I, a simpleton, can grasp. Circles as the limiting case of triangles, holonomy and path equivalence, group symmetries, how to think about permutations from a geometric perspective. I have to admit, I've invited him partly for selfish reasons. Whatever I learned from Tali today, I know I'll be able to apply in my research tomorrow. But I'm told the tools he's developing are useful for not only programming and learning to code, but also causal and symbolic reasoning in other domains. So I hope you'll ask him about those topics and take away some inspiration for your own research as well. Tali, thank you for being here today.
Thank you so much for inviting me. And this is a real honor to chat to you all and yeah, share some of the stuff that we've been thinking about at the Wolfram Physics Project and that I've been thinking about, inspired by that. Yeah, so let me get to it. What I'm going to do is do slides, and then I might jump off onto the website that is describing some of the work at one or two points where I haven't had time to make slide material because there's just quite a lot, but most of it we'll just be looking at slides together. Okay, so let me bring up Keynote and let's go. Or can everyone see that all right?
Yeah.
You might want to
yeah. I think the aspect, this is actually as big as it gets for whatever reason. So I might stop sharing my video in the interests of like bandwidth, just making sure that the connection is clear. But I'll try to come back on when we discuss anything or if any questions. And please, anyone stop me at any point to ask questions or make comments. That's totally cool and makes it more fun for me if there's like some interaction and it's not just talking to a group of thumbnails. Okay, cool. So the task is kind of quite daunting. It's like, how do we try to rebuild some of the machinery that's been sort of honed and perfected over the last hundreds, or even if you want to think of it this way, thousands of years. And the machinery I'm referring to is the machinery of geometry, which is kind of like fundamental to so much of the way that we think about not only physics, but sort of modeling and applied mathematics and linear algebra and all of this stuff is sort of, it's really profoundly based on our intuitions and notions of continuous geometry. So that means geometry in which there's no granularity. It's like smooth, you can zoom in as much as you like and things really don't change. And points have in effect infinite amount of information in them because they are represented by real numbers. So, you know, we've got this way of thinking about things that is based on all of those foundations. But in some sense, those foundations are incompatible with the way computers work. And the more we learn about our world, the more it seems like notions of computation information are somehow quite fundamental and need to be taken seriously, and maybe should be used as a basis to rethink some of our ideas about geometry. And so I suppose what this project represents is a kind of one approach to doing that. And it does mean that to even get started, you have to confront philosophical issues about what geometry could or should be. So that's what I'll just talk about here for a moment. So I'm going to think about geometry as the logic of movement. And that means how does some object or configuration or system or agent move from place to place or from state to state? And states or places are just things that an agent or system can be in, right, at a single time. And at each of these states, there will be transitions that are available that take it to other states. Those transitions are atomic. And what I should maybe say there is that, I don't know why there's a bullet missing, but those transitions happen at kind of like, each transition is, as I mentioned, atomic, and that kind of implies that time is also atomic. It passes in sort of a series of discrete like clock cycles, much like how a computer works. So that's just how we're gonna would prefer to think about geometry. So the substrate for geometrical reasoning that I'm going to propose here is something that I call a Cardinal Quiver. It's a kind of graph. And in the interest of time, I'm going to abbreviate that to just one word, which is Quiver. And that might annoy a very small subset of mathematicians who already have a meaning for Quiver, but too bad. It's a nice name. So what's a Cardinal Quiver? Well, those mathematicians would say that a quiver is a directed multigraph, right? And for me, I'm going to add one little extra ingredient that turns it into a cardinal quiver, which I'll then call a quiver. And that's going to be the edges are labeled. So we can name the transitions, right? And moreover, these labels can be repeated. And it's very important that they are repeated, actually, because that gives us some notion of when a direction at one position is the same as a direction in another position. So these labels are, in a sense, discrete directions that can be consistently mapped from one part of the graph to another. Now, just to recall, a directed graph is obviously a graph in which the edges are oriented, and a directed multigraph is a graph in which you're allowed to have more than one edge between a pair of vertices. So that's a directed multigraph. And then we have the labels, which are the cardinals. Okay. Now, an important thing to emphasize here is that the way that I draw these quivers, these graphs, is not important. It's just the topology that's important. So I will often draw them in a way that brings out their latent structure, but that's not, I'm not smuggling anything in through the way that I'm drawing them, just to emphasize that point. So those are the same quivers. They just happen to be drawn differently. Okay. There's one additional ingredient that we're going to want to impose on these labeled multigraphs, which is that the cardinals must uniquely identify a direction. My phone made a noise, okay. And that means that if you add a given vertex, a given position, and you look at the cardinals that are available to you at that position, a given cardinal can't occur more than once. So what does that mean exactly? Well, these situations are all allowed. We have the cardinal C is available here to X, and it's also available to Y. And if you had Y, you can also take inverse C or anti-C, right? Which means that you sort of go backwards along this edge. You're seeing that edge in the opposite orientation to the way that it's presented here, and you sort of go backwards. That's fine as well. But what you can't have is two ways to take C, to move in the C direction from a given vertex. So this is not allowed because there are two ways to move in the C direction from Y. And this is not allowed because there are two ways to move in the anti-C direction from Y. So that's the constraint. I'm going to call that local uniqueness. So let's look at some really simple examples. This graph has got three vertices, and there's only one cardinal, which I call A, and it just takes you round and round and round. Here's another example. It's kind of interesting because if you take any one of these, you will just bounce backwards and forwards between two vertices. And moreover, there's some vertices where you don't get to take a given cardinal. So if you're at vertex Y, you can't take the C cardinal because it's not available there. But that's okay. we just have to have a maximum of one way. We don't have to have a minimum of one way of taking each cardinal. Here's another example that's a totally legitimate cardinal quiver. Okay, now when we've got multiple edges between two vertices, just in the interest of like drawing it concisely, we will often collapse those and then just repeat the arrowhead with different coloration to indicate which cardinals are on that edge. So an edge can have multiple labels on it, but we know that that's a shorthand for there actually being multiple edges that are all between the same vertices. So, for example, this is the long way of writing it, and this is the short way of writing it that collapses those edges into one edge visually. Okay. Now, how many of these quivers are there? That's an important combinatorial thing to do just before you really even go any deeper than that. You just might ask, like, what's available, right? And it turns out there are a lot. So the way you can enumerate these is by just starting with these sort of naked graphs that don't have any orientation on them. And then you can enumerate those fairly easily, and then attaching all possible orientations. So these are like skeletons. And then we attach cardinals in all possible ways. So for example, there's only one skeleton. That's not trivial. And that's so one vertex, and it's got a self loop. And then you can just start attaching cardinals to it. And you can attach as many as you want. You just keep going. But obviously, there's not much choice in how you do that. Each additional cardinal, there's only one place it can go. You might say, why don't I have red pointing this way and blue pointing in the opposite orientation? And the reason is that the actual absolute orientation of the cardinal doesn't matter, because you could just rename red to be anti-red and nothing would change. All of the logic of what you do afterwards would be the same. So as long as you do a global flip, then you have the same underlying cardinal. It's just decided to rename it. That makes it quite difficult to enumerate these, by the way. There's no nice, as far as I know, enumeration, kind of closed form enumeration of how these work. So you can do this and you get large lists of these things, and you can just see it explodes, right? I've computed this at some point, and things do rapidly spiral out of control. My laptop can't handle anything bigger than 5 cardinals, and even within 3 vertex skeletons, you can't brute force it. And I'm not even brute forcing it. I'm using all kinds of clever symmetries and stuff to make it more tractable. But one benefit to even doing this, other than being an interesting academic exercise, is that we can certainly look at particular, and I'll switch to the website for this. We can look at particular cases, and we can just see if for a particular skeleton, whether there's a like a closed form for the number of cardinal quivers as a function of the number of cardinals. And it turns out that there are. So, for example, if you start with just a single edge and you just start enumerating these guys, then there's a nice closed form for that. I haven't proved it's a closed form, but it's sort of pretty obvious that it is, just that the sequence works for many hundreds of places. But it's not, as soon as you actually just say up to a certain number of vertices, how many cardinal quivers are there, that's not in the OEIS. So that means that no one has ever come up with a interesting enough mathematical situation in which the particular integer sequence of the number of cardinal quivers emerges. And that is an interesting sort of clue that whatever these structures are, they probably haven't been found in some slightly different dyes before. Otherwise, they would be in the OEIS. People are usually quite thorough about putting these kind of combinatorial sequences up on the internet when they find something interesting. Go ahead.
Yeah, I have a pretty basic question with regards to the cardinality. You have in your sort of your graph, you have like this bar on the edge. What does that represent?
That means that there's actually an arrow going one way and an arrow going the other way. So you could do it as like 2 arrows or a diamond even. Okay. But it's even shorter if you just do a bar. It means that like if you were to take that cardinal, you'd bounce backwards and forwards.
Oh, I see. I see. So it's just a shorthand for diverging cardinals.
A double-edged cardinal, yeah.
Okay.
Okay, all right. Now let's look at really regular quivers. These are quivers that are kind of obvious just from first principles. You don't have to think about them. There's nothing fancy going into defining them. But we do want to just give them names and parameterize them. So the reason I use the word transitive is that one property of these quivers is that in the neighborhood of any given vertex, things sort of look the same. And in fact, the quivers look the same everywhere. It doesn't matter if you jump to a different vertex. You can't really tell that that's happened if all you can do is explore your local neighborhood. So that's the sense in which they're transitive. So these are kind of like boring and also convenient models for space. They're sort of chessboards of different arrangements, tessellations of different kinds. So let's take a look at some of the simple ones. So we already saw this. It came up when we were making the small quivers. And these are called bouquet quivers. And what these are is single vertex quivers with just a varying number of cardinals on them. So bouquet with 3 cardinals or 4 cardinals. They're as small as cardinal quivers get, basically. If you don't draw them by collapsing them, then they look like flowers, which is why they're called bouquet cardinals. And I didn't invent that name. The corresponding graphs are called bouquet graphs. Okay, and then again, the most obvious thing you can do is just make a giant line of one vertex leading to another, and they never loop back or anything. And that's the line quiver. And we can parameterize it by how many vertices there are. So the kind of one that's actually transitive is the one with an infinite number of vertices. But you can also truncate, and you can just have 1 vertex or 2 or 3 and so on. Those aren't actually transitive, because if you're on the edges, then you can tell you're on the edge because you've only got 1 neighbor instead of 2 neighbors. Okay, then we have cycle quivers. These are circles. So they just take a line quiver and connect up the 2 endpoints, basically. And there's a degenerate case here, which is that the cycle quiver, the infinity cycle quiver is the infinity line quiver, right? If you have a cycle that never rejoins because it's infinitely long, then it is a line quiver. Then we have grids. Again, you have the finite ones that have a certain number of vertices, and the way I'm counting the vertices is along the edge. So 1 vertex along a side, 2 vertices along a side, and so on, 4 vertices along the side. And then the infinite one just goes off. And I'll often use this kind of idiom, visual idiom of like they fade off on the edge to show that it keeps going forever. Okay. And the one that's like maybe a little bit less common in our daily built environment and the things we make is, I mean, although you see it plenty of times in patterns and things, is a triangular quiver. And this is what it looks like. Each vertex has 6 neighbors. And they have this very regular form. And the cardinal structure, by which I mean the way that you've attached the cardinals to the graph, the underlying bare graph, means that if you focus on any particular vertex and then only take that cardinal, you'll get a line quiver. So there's a sort of blue stripe going up here, and there's a green stripe going that way, and a red stripe going the 3rd direction. Okay, and that's the infinite one. And then this is a sort of like 3-dimensional generalization of the square quiver. It's a cube. Again, this edge, finite ones will have a finite edge, and then they can also go off to infinity. That's the infinite one. Okay, now there's actually loads more, and you can, even in 3 dimensions, there's really interesting ones that relate to crystallography, which I just won't go into because things are plenty interesting, even with the ones we've already looked at. And then there's a real special case, and that is infinite trees. So let's look at that. So here's, now this is very, very general because it's parameterized by 2 things: the depth of the tree and also how many cardinals are available at each vertex to take. So let's look at that. So here's, it's a 2 cardinal tree. So there'll be 2 cardinals we can take at each vertex. Depth 0, you can't go anywhere. Depth 1, you can make 1 step. right? So if you start in the middle, you can take red or blue, or anti-red or anti-blue. So it's not quite the same as when you think of a rooted tree. It's not really the same. It's sort of got a center point and it goes in all directions out from that because you have these anti-cardinals that are also available to you. And then depth 2, you can take an additional step. And notice that if you take the red cardinal here, you can't, if you take anti-red, you're actually back where you started. So you only really have 3 novel choices available to you if you don't want to backtrack. And then, you know, it gets harder to draw these because there's an exponential number of vertices at a given as a function of depth. Okay. So the next thing we're going to do is just, oh, sorry, I accidentally went back. It's an annoying feature of Keynote. If you press back, it resets it. Okay, so now we're going to lock the number of cardinals. We're going to lock the depth to 2, and we're going to slowly increment the number of cardinals. So we had a 1 cardinal, which is a line. Now we have 2 cardinals. It's a kind of like square. 3 cardinals, and it's sort of triangular-ish, right? The snowflakey. And then it gets more and more and more branchy, and so on, right? Okay. Nothing very amazing there. Now, the next thing we're going to do is think about dimension. It's sort of visually obvious that these things had different dimension in some sense, right? Some were 1-dimensional, 2-dimensional, they plotted nicely on a plane, and then others you really had to like visualize them in 3D to see it nicely. What's going on there? Can we formalize that a bit? And you definitely can. And the way you do that is you pick a vertex and you sort of grow a ball of vertices that you can reach with a given depth. And you see how the number of vertices in that ball scales with the depth. So let's actually do that. So this is just a little animation that shows increasing the radius. So you see r equals at the top, and then n equals will show you how many vertices you have at that depth. And notice that for the 1-dimensional case, it sort of grows linearly. For the 2-dimensional case, it grows more than linearly. And then for the cubic quiver, it really does grow even more non-linearly, right? Obviously, there's an exponent there that will tell us something about the dimension. And that's how you get out the dimension. What you do is you find the closed form for the number of vertices within that ball. And these are what those closed forms look like for the various quivers: bouquet, line, cycle, square, triangular, cubic, and tree. And then you look at the Taylor expansion. So you say, what's the leading degree? So, I mean, you don't really need to do the Taylor expansion with this guy because these are already polynomials. For all of these guys, because they're already polynomials, right? But for this guy, you will. But for these guys, you've got an r and an r, so it's r squared. So that 2 is telling you that it's dimension 2, basically. For the tree, there's no leading term in the Taylor expansion because it's an exponential. So you end up getting, in some sense, an infinite dimension, right? And that accords with how people generally think about infinite dimensional spaces. Okay. Let's.
Do you mind if I ask a question there? Do you have to choose a basis, a coordinate basis for that to work? Or does that can that vary across your space? Like if you don't start at the origin, or if you start somewhere else, is that invariant, or do you assume that that definition of dimensionality it should hold everywhere?
Because these are transitive quivers, meaning it really does, wherever you start, it doesn't matter. They look the same everywhere. You can do this ball growing process. It doesn't matter where you do it. You'll get the same result. So they, in that sense, they sort of by definition have a fixed dimension. But for some unknown quiver that's you got from some computational process that may be finite, for example, then yeah, you can totally have different dimensions in different places. But it's a bit tricky because it's the scaling that really tells you what the dimension is. And that scaling is an asymptotic quantity. So the way that the ball grows, it may grow slowly in the beginning and then rapidly for a bit and then slowly again. And that in some sense means that there's a kind of spectrum of dimensions. There's no single dimension that characterizes this ball growing process. So dimension becomes a scale dependent property. Something could be locally two-dimensional and then like medium, medium regionally, three-dimensional, and then whatever. So it's interesting, but even how to think about that is subtle.
Yeah. So in some sense, you care maybe about the rate of change as this radius grows from your origin. Maybe this ratio kind of scales non-linearly, or that quantity you can compute up to a fixed depth, and it has. Is that always tractable to do, depending on the cardinality or the size of the branching factor?
It may be very difficult to compute, especially if there's lots of local structure. Even to get like things to smooth out nicely, you might have to go to large sizes to even see something. It might bounce between 1 and 8, as you go from depth 1, depth 2, depth 3. So it could be very difficult. Yeah. I mean, strictly speaking, it's not even defined. There's no scaling factor at a particular depth scale, right? Like you have to write out the closed form before you can even pick out that exponent. Okay, so I want to switch gears and talk about the kind of like the most basic mathematical tools that you use to think about quivers. And it's like when you think about continuous spaces, you think about things like continuous functions between spaces, right? Between topological spaces, for example. And maybe you think about differentiable functions and this kind of thing. It's like the bread and butter of analysis and differential geometry and so on, right? So how do we get started on this for graphs? Oh, this should say groupoids and groups. Sorry, not groups and groups. I'll need to do a tiny bit of group theory. I won't dwell on it too much. Just a recap. So recall, a group is a set of elements, and there's some kind of group multiplication that lets you combine 2 elements and get another element. And that binary operation has certain properties. So it's associative, which means it sort of doesn't matter if you've got a sequence of things you're combining, it doesn't matter what order you combine them, as long as you maintain the order of the sequence. You can combine the last 2 first and then do the other side, or you can do these 2 and then this one. The tree that you use to evaluate this sequence of group elements to make one final group element, the order of evaluation of the tree is irrelevant. The order of the elements might matter, like you can't swap them, but it doesn't matter how you parenthesize them when you evaluate them. That's the core idea. And that means that if you want to multiply a whole sequence of things, you just write down the sequence. You don't have to bracket them. So it's a sort of sequence of group elements multiplies to make another group element. Groups also have an identity. It's like an element that does nothing. So it will just multiply with another element and it just leaves that element unchanged. And also groups have inverses. So every element has a sort of anti-element that when you multiply it with the anti-element, you get the identity. And the identity is the neutral element that does nothing. So like really boring examples of groups are the integers under addition. 1 + 2 + 3 is the same as 1 + 2 + 3. And 0 is the identity, because if you add it to something, it doesn't change the thing. And the inverse of an integer is the negative of the integer, because that will yield 0 when you add it to the integer. Okay, but groups come up everywhere because symmetries are described by groups. So whenever an object, you can do things to an object that makes it look unchanged, the set of things you can do can be combined. You can first do one thing and then do another thing and then see that compound action as a single element. And you can also undo anything that you can do. So That means that groups are everywhere and they're just like a fundamental, crucial piece of mathematics. So there's another simple example. It's like integers modulo 4, integers addition modulo 4. So 2 plus 2 is 4, modulo 4 is 0. So if I look up in this table, 2 plus 2, there's 0. And like computers really love this stuff, right? Because you can, all the machine types, all the integer types in a modern computer, you can do the stuff very cheaply. You can do integer addition and multiplication modulo the size of the 32 bits or whatever. Okay. Now, the thing we're actually going to need is not a group. It's something called a groupoid, which is like a more chilled version of a group. And groupoid, the only thing that differs with a group is that sometimes you're not allowed to combine things. So it's kind of like if you had certain, a good example, certain symmetries that are somehow incompatible because they preclude, if you do the one operation, like you spin a cube in a certain way, maybe it winds something. The cube is attached to the table with a string, and as you wind the cube, it becomes impossible to wind it in the other way. You can still undo it, but you then can't do some other rotation, maybe. That's just a made-up example of a groupoid, right? So there'll be a subset of things that you can combine, which people often write G to. It's a subset of pairs. And things get radically more interesting when you consider groupoids. So for example, you can have many identities, not just one. So you can have some identities that work for certain elements and other identities that work for other elements that will be no-ops, but they maybe don't work for everything. They're not no-ops for every element. Groupoids are just generally much less studied. Sorry, that was what I last point to make there. Okay. That's just a little preamble, which we'll need because now we're going to talk about paths. So a path in a graph is a sequence of vertices connected by edges. So people write them like that. Vertex X goes to vertex Y goes to vertex Z. And those arrows that represent the certain edges that are meant by that arrow. So you might even have to have a label there if there's more than one edge between X and Y, for example. So in the cardinal quivers, path is the same thing. But because you have access to these cardinals, you can write them in a more compact way. So you can just say where you're starting and then write the cardinals and then say where you ended. And even that is optional because it's unambiguous where you ended, right? The local uniqueness property is what guarantees that you can fully describe the path just through the cardinals, because there can't be more than one way of interpreting what a cardinal means in the context of where you are. Okay, let's look at some examples. So we're going to use this quiver, and here's a particular path. So I started at X, I took the red cardinal, and I ended at Y. And you can just verify that there's a little ghostly red arrowhead there. I started at Y, I took the anti-red cardinal, and I ended at X. So anti-red because I'm traveling opposite to that direction that the arrow is pointing. Started at X, I took red, and then I took green. Now I'm at Z. I started at X, I took red, I took green, and then I took anti-blue, right? Now I'm back to Y. Or I might even loop all the way around. I took red, I took blue, I took red again. This is a different edge, but it's the same label, identifies it. And then sort of important special case is I might not do anything. I might start at Y. You can see there's a black dot there, and then take no cardinals, and then end at Y. It's an empty path. Okay. There's a super obvious thing you can do if you have two paths, which is you can concatenate them. So you can say, I'm going to start with this path, and then I'm going to continue the path with this path. So I'm sort of glue those paths together. So I take X, start at X, take R, now I'm at Y. I'm still at Y, I take G, and now I'm at Z. And then what that tells you is that this is a binary operation. So you put in two paths and you got out a new path that is the compound path of those two things. Okay, but interesting point is that sometimes that can fail. Like here, I started X, ended Y, and then this path wants to start at Z, but I'm not at Z, I'm at Y. So I can't do this. I can't combine these two things. So it's not defined. This composition fails, and we can sort of abuse notation a little bit and say this is equal to special symbol bottom, which means not defined. Okay, and then, but if I just happen to flip around the order of those two things for this example, so I had red and blue here, and I flip them around, I've blue and red. Now this is defined, and it happens to be this thing here. Okay, which by the way, immediately shows you that this binary operation is not commutative. So when you combine two things, when you multiply two things, A times B, path P times path Q is not the same thing as path Q times path P in general. Lastly, we have a notion of inverse, which is you flip the path. So here we have X, RG, anti-B, ends at Y, and then the inverse of that is Y, B, anti-G, anti-R equals X. So what you do is you take all the cardinals, you reverse the order, and then you negate them, you invert them. So red turns into anti-red and so on. Okay, and you can verify that well, a first point, before we get there, empty paths are the identities. They act like identities. So here we have an empty path on X. And if you follow that up by another path that starts at X, you still have that same path that started at X, because the empty thing, it didn't do anything. So it sort of disappears. And the same goes with,
Yeah, I might be jumping the gun here, but I imagine that like you could probably extend this to like a quiver trail, right? Like I think a trail is like when you don't have repeated edges, right? In your path, in your walk. And I wanted to know if you have like a cardinal and an anti-cardinal, will that be considered like a quiver trail?
Well, I don't study trails, but that question of if you have cardinal and anti-cardinal is important, and I'm about to get to that. So hang tight. So just to recap the point here, if you have a path, like this path with just one cardinal in it, R, then it has a left identity and a right identity. The left identity will be the empty path that starts where the path starts. And then the right identity will be the empty path that is on the vertex where the path ends. Those act like identities because they don't change the path when you compose. Okay, so here's a simple example of just a multiplication table, just like we did for the group. So I've got a really simple quiver here. There are only 4 paths on it. There's an empty path on the beginning, empty path on the end, path that goes from left to right, a path that goes from right to left. That's the only paths you can make. And the way the multiplication table works is sometimes they compose, sometimes they don't, but you always get back one of these things. So this is a groupoid, and it's a groupoid and not a group because you've got these X's here that say this is not allowed, you can't compose those things. Okay. That's all I had to say about groupoids, is that the paths on a quiver. Oh, and I should have actually, my slides are I'm missing a slide there, I suppose, which is the point about cancellation. So here's the point about cancellation. Cancellation says that if you backtrack immediately, then it's as if you did nothing. It's as if that didn't happen at all. So if you have R anti-R or anti-R, for example, then you're allowed to delete the pair from the contents of your path, and it's as if it wasn't there.
Would that be considered an identity? Sorry.
Yeah, well, this yields an identity. So that's actually what makes inverses into inverses, is that you do the path, combine it with the inverse path, and then everything will, the backtracking, it will cancel pairwise, and you'll end up with an empty path, which is an identity. And that's why the backwards version of a path is the inverse in the sense of a groupoid inverse. So you're forced into this backtracking if you want this thing to be a groupoid. That's why it's a good thing to do. Okay. All right. KV quivers, yay, more group theory. And sorry, I'm now a little bit warmer than I was when I started, so I'm just going to take a quick moment to okay. So a way people often talk about groups, especially to like compute things with them, is with something called a group presentation. So group presentation is basically like, it's an accounting mechanism to how to think about the elements of a group. So it's a way of writing it as letters in what's called a word. So the letters you're allowed to use are these things called generators. They're the kind of alphabet. And basically, you can write any letters you like next to each other. And you're also allowed to invert some of them. So you say you can have G1, G2, G2, G1, G2 inverse with a little -1 at the top. That's a valid group word. And the idea is if you want to, it's sort of meant to represent the element of a group. So if you have two group words, which remember represent elements of the group, the way multiplication is represented is that you just glue them next to each other as a word and you make a bigger word, right? Then you cancel pairs. So if there are any inverse pairs like G1, G1 inverse next to each other, you're allowed to delete them. And then the next thing you do is you look at these things called relators, which are little recipes for how to simplify the word, right? And you try the relators to try to boil down this word to find a canonical form for it. But really the idea is that those recipes just tell you little replacements that you're allowed to do in the word that will turn it into a different word that still represents the same group element by definition. So don't worry, we will see examples of that. So really simple example is just the integers. So they have one generator, doesn't matter what you call it. Let's say call it X, and there are no relators. So this is a very easy case to think about. So now we're going to do, for example, make a word that's got nothing in it. It's empty. That's actually represents 0 in the integers, right? Now I have a word that's got XXX in it. That represents 3. And because if you have XXX and you want to multiply really is add here. If you want to add it to XX, you just smash them together. Now you've got 5 X's in a row. There's nothing to simplify. That's now 5. 2 plus 3 is 5. And then negative numbers are the inverses. So you've got X inverse, that's -2. And if you have X inverse, X, then those two cancel and you just got X inverse, so that's -1. So whenever you add a positive number and a negative number in this sort of group word representation, you might have some pairs that cancel, and then what's left over, you'll have like a net number of either X's or X inverses. And if you count them, it'll tell you whether it's, what the number is it's representing. So that's just a simple example of how group presentations can represent groups. And we saw the integers. Slightly more complicated example happens when you have relators. So here you have two things, X and Y. And I want you to think about the kind of a plane with like your Lego construction kit, whatever you're allowed to go, X will go across, inverse X will go this way, and then Y will go up, right? And the really important fact is that the relator says that XY inside a word is the same as YX. That means if you have, for example, XX, YY, XX, you can shift all the X's to the left. It'll still represent the same group element, because that's what the relator tells you is how you can change the word and still represent the same group element. So that's a canonical form. You've got all the X's on the left, all the Y's on the right. And then you can think of that as just being a pair of numbers, number of X's, number of Y's, right? And when you add them, you'll have XXX, YYY, XX, YY. Then the X's will kind of shuffle along thanks to the relator, and they'll all be grouped on the left, and all the Y's will be grouped on the right. And then they just add, it's like the equivalent of adding those two numbers element-wise in the little tuple in the pair. So that's Z2. That's the group Z2, where it's the plane under addition, where you have little vectors and you can add them and then they just displace. Okay.
I noticed these relators, they have this ordering. Is that important? the 1, 2 to m, 1 to n.
Mm-mm.
So you can
No.
choose whatever order you apply them in.
Yeah, and the actual recipe is that you can apply these relators are really telling you when two words represent the same group element. So it doesn't give you an algorithm for how to guarantee, like it's actually, I think, NP complete for a general representation to decide if two words are the same. It's called the word problem. It may even be uncomputable, I don't know. But in general, it's like you can't, you might have to use brute force to like try all possible relators and all possible orders, and then, oh my God, the word gets bigger and it gets smaller, and you can't tell, are you getting closer to telling whether these two words represent the same group element? It may be hard to know. So sometimes these presentations are computationally tricky to work with, but at least conceptually, they're a way of getting a handle on a group, on the behavior of a group. In other words, it allows you to multiply things. It may be tricky to figure out if things are the same. If you've got a result here and a result here, are they the same group element underneath? Often they are. And the cases where they are is when you can compute what I refer to as the canonical form, where there's some simplification process where it'll always stop, and you've got the canonical form of a group word that's like guarantees that, because then all you do, if you have this element over here and this word over here, this word over here, and you want to say, are they the same group element? You find the canonical form for this, you find the canonical form for this, and then check if they're the same. And if they're the same, then you had the same group element. So when that's the case, yeah.
No, go ahead.
Well, when that's the case, group presentations are great because that's like anything that you could calculate about the group. Like in terms of, you can multiply things, you can find inverses, you have equality. Like if you're implementing it as a class in a computer, you've got to do like def __ equal __. Like you can do that, and you can do multiply, and you can make all possible group elements by just crunching through all possible words. You just make longer and longer words, and then eventually you'll start finding that you're making the same ones. So like it gives you a way of working with the group computation. So that's one of the reasons group presentations are important.
Makes sense.
At least for finite groups. For infinite groups, I mean, infinity is not nice, right?
So what is the representation of a group? Is this the same thing, or a presentation and representation are different things?
They're different things. Representation is interesting. It's a way, it's similar because it's a way, you've got the abstract group, like, I don't know, a cyclic group, right? Or symmetric group. And it's like, well, what is that? Well, a presentation is a way of like computing and like saying, well, here's how it behaves, right? It's like a modeling what the group does. And then a representation is the same kind of thing. Like you can see how the group behaves, except the tools you use are vector spaces and linear maps between vector spaces, right? I mean, more precisely, linear transformations of a vector space to itself, so automorphisms of a vector space. And those behave like group elements. They can represent group elements in the sense that there's okay, I don't want to get too much into representation theory. We do actually use it here, but later.
Sounds good.
Okay. So the cool thing is presentations like supernaturally give rise to cardinal quivers. And that's nice because it means there's like lots of interesting groups out there, and they all give very regular and structured cardinal quivers. In fact, I think transitive, but I need to check that. I think transitive. So the generators of the group, the letters that we build the words out of, they will act as cardinals, and paths in the quiver will act as group words, and the relators will tell us when two paths must lead to the same vertex. Okay, let me show you how that works. Oh, and yeah. Okay, so here's an example. This is a cyclic group Z3. So it's got 3 things in it. And it's like integer addition modulo 3, basically. So there's an easy presentation of this, which is got one generator, and you're allowed to, every time you have three of them collected together, they kind of blow up and disappear. That is how modular arithmetic works. Like every time you've got three copies of the thing, it goes back to zero. So, and it gives you a cycle quiver. Why? Well, because start with a line quiver. Every element of, and pick a particular vertex in the line quiver, that's your kind of base point. And that'll be where you measure paths from, okay? Any path in the line quiver will be either G, 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 or like anti-G, 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 one of those two, right? But we've got a special requirement, which is that if you do G, 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 that vertex has to be the same as the starting vertex, because this path must be the same as the empty path. That's what the relator forces you to do in this construction, right? So this is a construction. It's a recipe from taking you from a path representation, I mean, from a group presentation to a quiver. Right, so does that kind of make sense to you, to everyone? So like that, this a particular element here is the identity element. Oh, sorry, it might help me to give you an essential clue here, which is that vertices of the quiver are group elements. Sorry. So there are three vertices in this quiver because there are three elements of the cyclic group Z3. And when you apply the generator, it takes you from one group element to another. And the reason is you're adding on a cardinal, you're adding on a generator to the word. So here you have the empty word, right? You add on a generator. And now that gives you, it's a multiplication. It gives you a new group element, G. You add on G again, it gives you a new element G squared. You add on G again, you get G cubed, but the relator tells you that that's the same as the empty, as E, as the where you started. So the key idea here is you actually start with a tree that's got no paths that reconnect in it, and then you connect those vertices that the relator tells you have to be connected. We'll see more examples of this and it'll hopefully become a bit clearer. So this is actually a simple example. This is just the integers. So this has got presentation x1 or whatever. And all that this is saying is that whenever you add on the generator 1 to your group word, you get another group word and it is distinct from all the other group elements. So here you have 1, here you have 1 plus 1 is 2, here you have 1 plus 1 is 3, and so on. There's no reconnection because you can keep adding on, you can keep making longer and longer group words, and they will never be equal to any other group word. They'll never represent the same group element because there are no relators. That's the key point. Now here's an example that's more interesting. So this is the plane of Z2, right? Integer plane. The relator says that if you've got a group word and it's got X and Y next to each other in that order, you can flip them. And that helps us make a canonical form, which is we put all the X's on the left and all the Y's on the right. And that's how we saw it was a plane, right? It was a tuple of two integers, basically. And the reason that you get a grid graph out of this, and by the way, this goes off to infinity. It's not a square, it actually is infinite. The reason you get a grid graph out of this is that let's look at a path. Let's start 0, 0, which represents the empty path. We're going to take X, sorry, 1, 0, that's X. So just how I'm drawing it here. Take X and then take Y. The relator says that that has to give you the same vertex as taking Y and taking X. So those two paths, the XY path and the YX path, no matter where you start, must lead you to the same vertex. And this grid graph is the quiver that achieves that with no additional constraints, right? That just generates this grid graph. Now, here's something a little bit less trivial. We've got 3 generators, X, Y, Z, and they commute. So you're allowed to flip X and Y, and this is just a shorthand for saying X, Y equals YX. They're allowed to commute. So X, Y is YX, YZ is ZY, and XZ is ZX. But there's one additional, if that's all you had, if you chop things over here, okay, you would have a cubic quiver, because you'd have just like a grid, but with one extra way to go, right? You'd have 3 integers. But this little secret recipe here says that, this relator says that you can, if you go in, and these are RGB, I should have called them XYZ, but you get the idea. It says if you go R and then you go G, it's the same as going B. It's telling you that those 2 paths have to connect when they wouldn't normally connect. So they will lead to the same vertex. And there's actually a very nice way of interpreting it 3-dimensionally, which I will just briefly show you here. Cubic quiver 4. Okay, so here we've got, let me make this a bit bigger. Here we've got nice cubic quiver. What I'm going to do is I'm going to find an angle to look at this that forces that identification of vertices. That's a bad one. There we go. Okay, so what I'm doing by finding that angle is I'm actually finding a way of forcing a whole set of vertices to look the same, to become one vertex. And it amounts to saying that if I go in the X, and then Y direction, it's the same as going in the Z direction. You'll see that later with the linear algebra side of things. So it's saying like you project the grid graph down in a certain way, you quotient by a certain relation, and you get a triangle quiver. In a sense, that's where triangular quiver comes from. Okay.
Can you mention if there's any restrictions on this presentation? Like I notice here, things are kind of linear. They either stay the same size or they collapse. If you have like some rule that says XY equals XYY, or some rewrite where there's an expansion, is that a valid presentation of a group where you run into issues? Like, can you define any combination of
anything you want?
Yeah,
yeah, you totally can. But then you run into this problem that that it may be very difficult to find an algorithm that will give you a canonical form that will allow you to decide when two group words actually, because what I'm doing here, like the way that I'm generating these graphs underneath, so I'm starting with an empty word, then I'm saying, okay, what happens if I add an X to it? Now it's X, right? Okay, what if I add now I'm on a new vertex now, and it's connected with the X cardinal. Now what if I add a Y? Okay, now I've got the word XY. Okay, well, I assume I'm at a new vertex now because it's not the same as I measure. Is it the same as this? No. Is it the same as this? No. So I'm at a new vertex. Now, what if I add a Z? Now I've got XYZ. Ooh, I can apply one of my relators. I can replace the XY with Z. So now I've got ZZ. Well, it's still new. So like, you just run this. It's like a breadth first search, basically, of more and more and more group words where every time you make a group word, you check, have I ever made this before, right? And to know whether you've made it before, you have to actually decide, is this group word the same as another group word under one of the relators, or under any sequence of relators? Is there a way of rewriting the group word using relators so that because it's the group elements that you care about, right? The relators are just a surface syntax for them. So the group elements are the vertices. The vertices are supposed to represent unique elements of the group. And so in order to do that quotienting where we collapse vertices, we figure out when we've, in the breadth first search, we figure out when we've gone back to one of our previous vertices, right? And it's reconnected. To figure that out, we need that normal form so that it's really simple, because otherwise it would be it would be exponential. You'd have to check every new vertex against every single previous vertex. And each of those checks might be incredibly complicated, might never terminate, right? So like you can't even potentially can't even do it. So that's why you want that canonical form. And as you point out, if you're allowed to grow the word, if some of the relators will grow the word, and you don't know, like, is there a sequence of relators that will grow it and then it'll finally shrink, and you actually need to grow it first before it will shrink? Then it's like, oh my God, can you put a bound on that? That's why it's NP complete, I think, is that in general, like, you could encode the actions of Turing machines and things in this like problem of making the word grow and shrink and whatever. Like, you, I don't know, build a tape into the sequence, whatever. I don't know. I'm a little bit, it's not
if it's NP complete, then it would be decidable. But if you can encode a Turing machine, then this would be undecidable. So outside of this, but the nice thing about this linear form is that you have some sort of decidable or some sort of decision procedure about whether a given quiver is equivalent to the thing that's generated by this. Like is there an algorithm that decides whether some presentation describes say like a finite quiver in a polynomial time or something like this?
I don't know. I mean, certainly if it does describe one, you will determine that, right? Because you'll run out of, you'll try all the generate, eventually you'll start visiting nodes you've already visited, and then all of them will be the same, and then you know you've got a finite thing.
I see.
But I don't focus on this particular question, so I probably can't say very much more than what I've already said. Which...
Fine. So what comes first in your mind, the quiver or the presentation? Like, what do you usually?
Or the group.
The group first, and then those. I see.
Well, I don't know. I think in a sense the quivers come first, right? Because they are. I see the group presentation as a kind of coordinate. It's a very interesting question. There will be some things to say about it a bit later, because it actually relates to curvature. So when you want to make discrete, the discrete incarnation of curvature, the way to think about it is that you have a sort of patchwork quilt of different sections that each locally represent a Cayley quiver. So they locally look like the equivalent of flat space, right, which should be familiar from differential geometry. But then when you kind of move along the patchwork quilt, you can find out that via various bookkeeping mechanisms, you can find out that you can't glue them together to make a bigger patchwork that also behaves like a Cayley quiver. There's an obstruction. In fact, often those obstructions are associated with what a crystallographer would call a defect, a crystal defect. And it's those defects that are, in a very real sense, a source of discrete curvature. Like they are like a quantized origin of curvature, which is for me just like a mind-blowing idea, because it suggests, for example, that the continuous forms of curvature that we're familiar with in physics, if the Wolfram Physics project is on the right track, they could be at a fundamental level associated with kind of granularity of space, right? They could be associated with particular defects that might have some role, play some role in the presence of particles or whatever. And then like gravity makes a whole lot more sense, for example.
I see. All right. I didn't want to take you on too big of a tangent. Please continue.
Thanks. No, I mean, that was very interesting topics. Okay. And this is actually what I was getting. Maybe I should have even started with this particular presentation. This is a 2-element presentation with 2 generators and no relators. That means you can make any word you like, and the word does uniquely identify the group element. There's no, you don't have to compute anything to see if 2 words are this. They only represent the same group element if they're the same word. That's the easy part, right? And what that really is telling you is that you don't quotient anything, you don't connect any vertices. Every path that you could possibly make takes you to a distinct vertex. Every sequence of X's and Y's will send you to a unique place. That is what a tree is. So we have this nice thing that the Cayley quiver associated with the free group is a tree. The physics people sometimes call it a beta lattice. Okay, and actually, that tree is, it's the right way to think really is to start with that tree and imagine folding it to glue together the vertices such whose paths from some origin are identified by a relator. A relator tells you that those two paths should be the same because the sequence of cardinals, the relators tell you that you can get from one sequence of cardinals to another by applying relators. So let's actually look at that in action. So here we have the tree on 2 cardinals. And remember, that's the Cayley quiver of the free group, 2 elements. And then we're going to apply this relator. So what we're going to do is we're going to say every time there's a path that has xy in it and another path that is the same except it has a yx in it, we're going to, those 2 paths will lead us, the tree will tell us they lead to 2 different vertices because every 2 paths lead to 2 vertices. And then, but now we're going to say, oh, now we're going to glue them. And you can see how, what's going to happen. Like, so you had xy before, it took you here, and you had yx and it took you here, and these were distinct. And now if you glue them, you got a kind of face of a square. That's going to happen everywhere simultaneously. Everywhere you could make one of those incomplete squares, they will now complete. And you can animate this. So that's what it looks like. That's, oops, why is it only playing once? So it's taking us from the tree, which has got exponential number of vertices, down to the grid, the square quiver, that's got, you know, but quadratic number of vertices as a function of depth. And that's the folding process or the quotienting process that is like a key way to think about all of this stuff. Okay, that folding process is, I mean, graph theory, people know about this, it's called a contraction. So you just choose sets of vertices and glue them, and then all the edges sort of just hook up. And interestingly, contractions induce things called path homomorphisms, right? And what a path homomorphism is it's a way of mapping paths in one quiver into paths in another quiver in a sensible way, right? Because let's say that I have a map that sends paths in one quiver to paths in another quiver. It should preserve basic properties. Like, for example, if I can concatenate 2 paths, if I can compose 2 paths in the first quiver, and then they get mapped somewhere, I should still be able to compose them in the second quiver. It shouldn't disconnect them because they share a vertex, so that would be crazy. So if you just apply that consistency condition, it turns out to be very straightforward algebraically. It is the requirement that you have a groupoid homomorphism between the path groupoid of the one quiver and the path groupoid of the other quiver. And what these contractions end up doing is they are they're path homomorphisms. And the kernels of those path homomorphisms are actually the relators. So the paths that are sent to empty paths are precisely the paths whose contents are described by those relators. Maybe that's a bit abstract, but we'll get into that. Now, there's a beautiful thing, and probably we're running out of time, so there's a lot to get to, so I probably won't go into too much detail on this, but that story I told you about Cayley quivers generalizes to not groups, but something even richer area of mathematics called group actions. What group actions are is they're a combination of a group and how it behaves on some set. So the group can act on a set. A good example would be if you have a rotation group, like the circle rotation group, that's just spinning something around. Well, you can spin different kinds of objects around. So if I spin a cup around, right, then I have to go all the way around the group, all the way around space once before it looks the same as it did before, right? So really, the way that it acts is, you know, it's a faithful the way you would say it is it's a faithful action of the, faithful action of that group. But if I was acting on a circle, Well, it's kind of a bit pointless because a circle is it's so symmetric that if I rotate the circle, it looks exactly the same as it looked before. So the way that the group acts on the circle, if I have, rotations in mind, I have plans that I want to rotate it this much, or I want to rotate it the other way. And then I'm like imagining, let me first combine the plans in my head before I actually do the rotation on the circle. None of it matters because anything that I do to the circle leaves the circle looking the same. So the action is the identity, right? Like that's how I would be able to act on a circle. And that's called a trivial action, like it doesn't do anything. So as soon as you couple together a group and then some set or space that's acting on, there's quite rich behavior there that relates to how much information does the intricacies of that action on the set, how much information does that preserve about the structure of the original group? Does it preserve all the information or a subset of it, and so on? So when you do the equivalent thing with quivers, here's a good example. So what we're going to do here is we've got 3 colored playing cards or beads or jelly beans or something, and they're in a row. And we're going to think about the group of transpositions we can do. So this is the symmetric group of 3 elements, basically, right? You can permute the first 2 things, you can permute the last 2 things. And it turns out by combining those permutations in different ways, you can achieve any permutation that's possible, right? That's called the symmetric group on 3 elements. And choosing these 2 particular transpositions, that's a choice of generator, okay? Which means that I have a presentation now because I've got these 2 generators and I've got some relators. I don't even know what they are, but I've got some relators that tell me how they interact with each other. And what I'm going to do is I'm going to apply them to the 3 colored playing cards. So I've got green, blue, and red. What happens if I permute the first and the second card? Well, then I'll have blue, green, red over here, right? So this edge of the cardinal quiver is telling us what happens when I apply this permutation, this transposition. And if I do it again, I'm back where I started because that's what happens when you swap 2 things again. It goes back to being the same. But notice I can get all 6 different permutations of those 3 playing cards by choosing to apply these transpositions in different orders. So this is a group action because we're seeing how it behaves on some particular set. And what's really interesting is that there's like a strange geometry here. So for example, if you apply it to, if you do the same thing but with 4 elements, so you've got 4 colored playing cards and you're just applying them in different ways that with these choices of transposition, then you actually get, I can't remember what the name of that the polytope is. Hold on a second. It's called a permutahedron. Okay, it's the truncated octahedron. Sorry, I didn't know that offhand, but kind of fascinating how a purely combinatorial setup gives you a recognizably 3-dimensional geometric structure, or at least a graph of it. And what's interesting here is that you can have degeneracies. So you can have, let's say you have 2 red playing cards. Well, depending on where those are, if you swap them, you can't tell that anything happened. So let's say they're in the middle here. You can see that in this vertex here. If I swap 2 and 3, in other words, if I apply the blue cardinal, nothing happens. So there's actually a self loop here, which I'm not showing, but this is no longer a Cayley quiver because that's not how any group behaves. Every group element, when you multiply 2 group elements, you can't have them, unless one of them is identity, it can't be equal to itself again. So this is not a Cayley quiver. It's definitely not a Cayley quiver, but it's similar, right? Like it's an action quiver is what I call it. And this is really fascinating because it immediately gets us into how you can use a lot of the same ideas, but where groups are no longer the right way of thinking about something because of certain degeneracies. You can have some structure where maybe you're not allowed to perform certain operations, or because of certain symmetries, those operations are not perceivably different. And that's where Cayley Quiver can still bring out that geometrical structure where a group would just simply fail, right? Okay. There's a way of thinking about how to build. I think I'm gonna skip this part actually, because there's something else I want to talk about here. So all that this thing is about is formalizing the idea of, it actually is, this is the representation theory part rather than the presentation theory part. So the very basic idea here is, if you associate cardinals with matrices, right? And then you make all possible paths on this thing called a fundamental quiver over here. So you just like all the ways that you take blue and then you take red and then you take blue again and then you take blue again and then you take red. That's a path. And you can make a matrix that is the value of that path by just multiplying together all the matrices associated with those cardinals. So, you know, there's just in a sequence. And when you do that, you get a value out, and that value tells you it is a label for the vertex that you should be ending up at in this thing. And it's another way of achieving that. Basically, what it does is it achieves that quotienting operation. It's very similar to this whole idea of presentations. It's just computation encodes the process of finding that you like exploiting the fact that there's a canonical form and you can represent it as a matrix, and the way the matrices multiply is a representation of the way the group acts, which means that instead of working with words, you can work with matrices. That's the basic idea. And you get out all the same stuff. But also what's nice is you can play with the matrices and take things that have nothing to do with groups, and you can still get out quivers from this kind of thing. I'll show you something here. And by the way, there's a little important point here, which is, notice over here that to get the triangular quiver, one way you can do that is you can have matrices that effectively, each of them will add 1 to one coordinate and subtract 1 from a different coordinate. So I don't know how much hard-coded knowledge you guys have about how matrices of this upper diagonal form act, but these are basically, they represent affine translations. They represent translations, basically. The matrix it's much more complicated than it needs to be in a sense, because all it's really doing is just adding things. So you'll start with an identity matrix that represents the empty path. And then every time you apply one of these matrices, it'll just add 1 to the top right or subtract 1 from one of the other 3. So these top 3 cells will act as coordinates, basically. And I'm writing out these coordinates over here. So that's the identity matrix down there. And then if you, for example, you follow red, what is that doing? It is adding 1 to the first coordinate, subtracting 1 from the second coordinate. So you can check that. It's adding 1 to the first coordinate and subtracting 1 from the second. This is -1. And it turns out that gives you the triangular quiver, essentially. That is actually the only reason I'm highlighting this is I want to show you something about that just now. So let's remember that. Okay. One quick thing about why you'd want to even think about these matrices is that if you preclude certain paths, if your fundamental quiver that you're using to generate all these paths before you quotient them, if it doesn't have one vertex, it means that you can't form certain words, right? So here we have 2 vertices, and you're allowed to take any of blue, green, or red. But once you're over here, you can't take blue, green, or red anymore. You have to take anti-blue, anti-green, anti-red if you want to keep extending your path. And what that does is it means that you have half the choices that you normally have available to you when you are moving around, when you are building these paths. So you go from a triangular quiver, you effectively cut out half the vertices. And that gives you a hexagonal quiver. So that's a very nice thing, because it tells you you can get richer structures from much the same process by just doing this quotienting operation on a more complicated quiver than a bouquet quiver, which is the simplest possible quiver. So it's a rich toolkit for just generating geometries here that still have a certain amount of regularity, but they're kind of a little bit more like Swiss cheese, right? They've got some forbidden parts in them. Those are called intransitive lattices. Okay, I've talked about path homomorphisms. I'll get to curvature in a second. I want to talk about rewriting systems, and then that's probably, are we probably getting to the point where I should stop? I think we've.
Okay, yeah, that's. Do you want to end it around 1:30? That way we can have some time for questions, and I know there's other topics people want to talk about. So.
Cool. Yeah. So, very quick about rewriting systems because they connect to quivers. What are these? That's a mathematical sort of model of, originated as a mathematical model of algebra, and it was particularly useful in formalizing just the syntactical operations you do when you do algebra, and what a computer algebra system like Mathematica, what it does when it tries to do math, right? When it tries to do symbolic mathematics. And in fact, Mathematica as a computer language is a rewriting system, which is very unusual. Most languages are not rewriting systems. Okay, so what I'm showing you here is, it's not technically what you would find in a computer science book about rewriting systems. It's sort of what makes most sense for the kinds of questions I'm interested in. Got a bunch of global states, got a bunch of rewrite rules, which tell you how to rewrite a state into another state. Those rewrite rules can be non-deterministic in the sense that there can be more than one rewrite rule that can apply in any given situation. So a global state could be rewritten several different ways, and it's just not defined. There's no right way. They're all good. A potential application of one of those rewrite rules is called a match. It's like when a certain pattern occurs, you can rewrite it. That's a match. If you do the rewrite, then you have a new global state. And when you have a global state with no matches, then it's kind of halted. It's nothing you can actually, it's kind of stopped, right? There's nothing more to do to it. Now, this is manifestly a graph, right? Because when you have these states, the rewrite rules tell you how to connect them. They tell you which states lead to other states under given rewrites. And the sources, the vertices with no incoming edges, are, in a sense, the initial conditions of some kind of dynamical process. And the sinks, the halting states, are the sort of final conditions where sort of the thing is finished, right? Now, if you make a path in this graph that follows the order of the arrows, it's oriented the right way with respect to all of the edges, then that represents a possible evolution of the system. It's something the system could do if it was, if you were seeing it as a non-deterministic automaton and it's just doing some running and doing something, and then maybe it stops or maybe it goes on forever, but it'll produce a sequence of states. And that sequence of states is a path in the graph and vice versa. Now, I'll just give you a sense of the breadth of all of these. You can have string rewriting systems, you can have Turing machines, you can have asynchronous cellular automata, you can have multi-state rewriting systems, you can have graph rewriting systems, hypergraph rewriting systems. They all kind of fit into the same general machinery. And some of them are universal in the sense that they can emulate other rewriting systems. So in particular, hypergraph rewriting systems are universal. You can embed any other rewriting system into hypergraph with suitable asterisks. The one I want to tell you about is string rewriting systems. They're quite simple, but still almost impossible to analyze. So global states are strings. Rewriting rules are replacements of one string with another. Oh, I hate this. Replacements of some substring with another substring. And because there can be more than one place that a substring occurs in a given string, that's where the non-determinism comes from. So let's look at an example. We'll have an initial condition that will be black, black, white, white. The rewrite rule will send black, white to white, black. So it'll look for that substring black, white and replace it with white, black. And they will sort the dark characters to the left of the string, or at least they'll sort a dark character one step left to the, overall. Okay, so let's do an example. Dark, dark, light, light. There's the match, because that matches our left-hand side of our rule. Okay, we apply the rule. Now there's a match over here. We can apply that. There was also a match over there. We can apply that. Now there's yet more matches for these new states over there. And it turns out that one actually it yields the same final state there, but there's still one more match. There it is, and we're done. And what this has done is it's literally sorted the string into lexicographical order, you know, like the dark characters are now to the right. I mean, I could use zeros and ones, but it's easier to see if you use colors like this. Okay, a really simple example. There was some non-determinism in a sense, because there was this kind of place where you could do either thing, but it eventually resolved. And that's the property that's called global confluence. There's also a form of that called local confluence. Some systems are not globally confluent. So here's an example. It's got two rules. Dark light goes to light dark, and also light dark light goes to light light light. And depending on which rules you decide to do when, you can actually get into three final states, all light or one dark at the end or two dark at the end. And it kind of makes sense because that's the behavior of the ordinary sorting system, where you never applied the second rule. And then depending on how many times you apply the second rule, you can remove any number of dark characters, and eventually you can have just only light characters. Okay. All right. The number of these the size of these graphs can really explode. And there's an interesting process we can do. I'm still wrapping my head around, and it employs hypergraphs. So the basic idea is this. So these blue and red things in the circle, the strings would be too long. So now I'm just sort of like doing them in a little arch pattern. It's just the same picture as I showed before, except now it's got three, you know, so it's length 6 string. I'm claiming that this thing is actually encoded by the structure over here. And this row at the top is going to represent that first string over there. Okay, so let's see how that works. This global state is equivalent to this composition of local states. These are little local states. And there's only one rewrite we can do, which corresponds to this black dot over here. When we do that, we get these two new local states, red and then blue. So look, blue, blue, red, blue, red, red, blue, blue, red, blue, red, red. Okay, and now the rule is anytime you see one of these black dots and its inputs are highlighted, then it can fire, and they will become unhighlighted, and then the outputs will become highlighted. So, for example, this input and this input are highlighted, and so this thing can fire. Now we've got this going on, and this corresponds to picking the left-hand match in this system and applying it. And you can keep going like this, and gradually you have this wave front of kind of local states that are active, and they gradually get transformed like that. And eventually you get dot, 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 you get down to the end, and then finally there's only one rewrite that's left, and it's over there. Now, what is the strange object here, and how did I make that? Well, it's a hypergraph. And the reason it's a hypergraph is that you can think of this black dot as actually being an edge, more precisely a hyperedge, where the input local states are sort of, when they are both, they're the source of the hyperedge, and the output local states are the target of the hyperedge. And, you know, it just keeps going like this. And this whole structure it's a particular kind of hypergraph. It's called a set-set directed hypergraph. So there are different kinds of hypergraphs. This is one of them. And it turns out this is something that's actually well studied in computer science called a Petri net. So Petri net is a kind of modeling formalism that's used in different places. And its connection to hypergraphs is, as far as I'm aware, not widely appreciated, or people just haven't bothered to make that connection. And this duality is really just that it's the bipartite graph structure of the Petri net encodes vertices and hyperedges of a hypergraph, the rewrite hypergraph. So there's this question now, which is unsolved work, which is what is the sort of hyperpath groupoid or hyperpath algebra of these kind of hypergraphs that will let us understand the behavior of arbitrary rewriting systems or particular rewriting systems? That's a very interesting and challenging question. I need to skip this. I want to show you, I don't have time. I think we should leave it. one of the things I wanted to talk about, just so everyone's aware, that, and maybe I can get, how do I get back to, oh, I suppose I just close this window. So one of the things that I wanted to talk about a little bit, you can see this slide deck is way out of control, is that you can do very interesting modeling with even the simplest kinds of rewriting systems. So for example, I think I had it on the big table of examples of rewriting systems. So multi-set rewriting systems in which all you do is have a set of tokens where repetition is allowed. And the rewrites say, if I have 2 tokens of this type and 1 token of that type, I can rewrite them to be 3 tokens of this other type. If that's all you do, if that's all you allow, that is already a kind of discrete generalization, a sort of stochastic generalization of ODEs. So you can get out things that in some senses are better models for biological processes, like for population dynamics, than the traditional ODEs that are studied in, you know, population dynamics. So like Locker-Volterra equations and those kind of things. They have weird aspects to, I mean, it's nice that you can solve things in closed form and so on, but they also, for very low population numbers, if there's just 3 tigers and you're trying to model where the tigers are going to go extinct because they don't have enough prey to feed on, then it's actually, you can't approximate that as a real number. That's a dangerous thing to do because 2.5 tigers is not a thing, right? And the fact that they maybe need to mate in pairs becomes very important, right? So that's what's really nice about multi-set rewriting systems, is that they're effectively a mathematically rigorous way of thinking about agent-based modeling, but just mathematically stripping away all of the kind of arbitrary other stuff and just focusing on how do you take ODEs and apply them to discrete systems, basically. And you can do quite a lot with them. And what's really nice about that is that there's actually ways of thinking about how to generalize them to involve space and rich semantic dimensions. Like you could have genetic variation or sex naturally encoded, and it all falls out of hypergraphs. So you can think about multi-set rewriting systems as being hypergraph rewriting systems where the spatial component has been completely stripped out. So the only hyper edges have 1 vertex in them. So if you already like multi-set rewriting dynamics and you generalize to hypergraphs, hyper edges, true hyper edges, then this sort of rich explosion of behavior that can really do any kind of modeling that you can imagine that has at least got discrete qualities to it. Sorry, I couldn't go into detail about that because it is very interesting how that modeling process works, but maybe another time.
Yeah, maybe another time, Tali. Looks like you've prepared a lot of material here, and don't want to cut you short, but maybe some folks have to go places, and I want to have a quick Q&A for some questions that maybe prepared or the audience would like to ask. So maybe this would be a good time to give a round of applause to Tali for giving this talk today. Really appreciate it. Can we unmute you're still here? Okay, at this time, I guess we'd like to open it up to any other questions in the audience. If not, then I have a few. Okay, I guess I could get started here. This is kind of on my mind because you were talking about these generalized rewrite systems and higher abstractions. So you're kind of building this interesting tower of abstractions, on top of groups and so on. And I'm curious so you mentioned that there's computational complexity issues with even enumerating some of these quivers, and this is one thing that I'm kind of very cautious about in computer science, is you kind of consider very restricted cases of things that are computable, and you even then you get into trouble, like you're saying. So if it's the case that many of these things are equivalent, say like graph rewrite systems are Turing complete already, what additional value do you see for introducing more abstraction to this process? Is there some additional flexibility that you'd like to gain, or is it just a natural fit for certain types of problems that you can't express in, say, just a string, a Turing machine type formalism, or what is it? Is it just elegant? Do you find it elegant from an aesthetic perspective, or what appeals to you about these hypergraph rewrite systems that you're not able to do in less powerful formalisms?
Yes, no, thanks. I think one thing that's really, there are a couple things. So one is, and maybe these answers are a little bit preliminary because the mathematics hasn't been proved out yet, but one thing that I didn't go into today, and could be a topic of a whole talk, would be the connection between hypergraphs and multilinear algebra. So it turns out that there's a natural representation of arbitrary hypergraphs as kind of a tower of higher and higher rank arrays, or higher and higher arity arrays, right? And the way that you sort of combine these arrays, the way that they participate in multilinear algebra, has interesting connections to logic and to tuple calculi and relational databases and all kinds of things. So the idea there would be that multilinear algebra has really been a very powerful tool as we've understood more and more about how to sort of deal with it. It's kind of become a universal compilation target for a lot of problems, right, that people face in modeling and science generally, even mathematics. And we have sort of powerful ideas like diagonalization and eigen decompositions and all kinds of forms of how to decompose matrices, right? And much less is known about higher arity arrays and how to think about them, even though that the bread and butter of deep learning, for example. So if we can have a sort of a rigorous way of formalizing all kinds of, or gathering together many disparate things that maybe already people have a handle on how to do. An example would be agent-based modeling or Petri nets. But if we can sort of gather them in one place and develop a powerful toolkit of ideas from multilinear algebra with all of these problems to work on simultaneously and see the kind of connections and opportunities, then it could be quite a powerful and efficient way of tackling all of those problems at once, rather than having bespoke solutions for all these different areas. So I think that's one answer.
Okay, yeah, I think that's a reasonable way to motivate it. I'd like to ask a philosophical question, kind of maybe take a little step back, and in computer science, there's this temptation that maybe programs reflect some deeper mathematical truth. Something that appeals to a lot of computer scientists is the idea of a program that's a mathematical object. And in some ways, it feels like programs have these properties, but in others, they're kind of messy and full of flaws, right? Code that people write in practice tends to be maybe just a byproduct of some ephemeral interaction between the human machine. So I guess I'd feel remiss if I didn't ask you this, because this is the code reading group, the ML for Code reading group. But in your opinion, are programs designed, invented, or are they discovered? You kind of touched in the beginning about these combinatorial explosion, and we have some things that maybe reflect some deeper truth that have, some convergent properties. If I didn't discover it, someone else would have. Are programs the same type of things, or are programs something completely different in your mind? Are they?
Oh, that's really interesting. I mean, I think I know what Wolfram's answer would be. I mean, so one of the things that he's beaten the drum about for many decades is that maybe we invent programs, but there's certainly many programs to be discovered out there. So we have this sort of bias towards engineering in that we think, unless we can tightly control the design of our programs, it's sort of like nothing else is going to be waiting out there to be discovered. But certainly one of the things that maybe there's all kinds of work on, like super optimization, for example, has shown this kind of thing, and genetic algorithms and deep learning as well, that there are perhaps in some sense algorithms that are out there in algorithm space that can be mined, right? Whether through brute force search, enumeration, or through evolutionary processes of different kinds, or through gradient descent type methods. And for me, it's still like a little bit up in the air whether things that we assume are gradient descent, we assume is sort of like exploiting all kinds of nice, gradient signals to like find the good algorithms. Like if you think about a trained neural network as an algorithm, you assume that it's really crucial that it gets to exploit those gradients to do that, and presumably it is. But we still don't know how much of the optimization process is also doing kind of random search, right? And how much of it is there being, I don't know, there's a lottery of tickets that are hiding. I'm not super up to date with this research, but I do know it's a question a lot of people are kind of thinking about, and whether maybe there's a sort of surface level of continuous phenomena that has to be gradient descended through, but then at some point you might hit some sort of discrete knotty things that characterize the problem space or characterize the solution space that are actually better modeled discretely, right? It'd be better to have a sort of toolkit of little parts. Maybe gradient descent plays some role in discovering or honing these parts, but then at some point you also want to kind of like crunch them together in some better, well-defined way. Or if the problem space has got a discrete character to it, and arguably language is an example of that, there's room to exploit that. So bit of lesson aside, right? Like that question of like how much
hedge your bet.
Algorithms are, okay. How much algorithms are discovered or learned is like super interesting, is like very, I think, embedded in so many different things that are going on right now.
Yeah, that's interesting. I guess maybe this question of constructivism is something that I think a lot of type theory people and computer science people have thought about. And there are different ways to kind of model these problems. And so I think a lot of people maybe in your sphere have kind of looked at like category theoretic abstractions or different modeling systems for representing knowledge. And it's cool to see, that there's the computational aspects of, there's nice connections to maybe Mealy or Moore machines or Petri nets or different things in that can be instantiated in hardware. Okay, I wanted to ask one more question before we open the floor up to one last call. And that's about your path to independent research, and what led you down this journey. I think this is interesting from a personal aspect, as well as maybe others are interested in following your footsteps. So what was it about these kind of sorts of questions that maybe you can't pursue in a more traditional context? Maybe you mentioned in a previous discussion that you felt like you weren't as interested in category theory and you wanted to do something else. What other motivations or insights can you share about how it's been going, and any advice you can give to others who are interested in doing the same?
I think I might have actually changed my perspective a little bit about category theory, especially after thinking about some topics in higher category theory and how it relates to hypergraphs. So there's something I just discovered quite recently, is that there's this notion of opotopic sets and opotopes, which are a fascinating idea, like how to generalize these things called operads. And it turns out that the opotopic diagrams that are mathematician called Eric Finster invented to model these higher category theoretic situations, specifically around open hopes, are complexes of hypergraphs. So they're hypergraphs, they're sort of chains of hypergraphs such that each vertex in one hypergraph, or each hyperedge in one hypergraph becomes a vertex in the next hypergraph. And that sounds very abstract, and you may wonder what use it is, but it's actually crucially about modeling operations. So if you have some kind of process that's transforming things, it could be a mathematical process, it could be a computer program, whatever, and you think about ways of composing the transformations, and then ways of composing those compositions, the natural way to do that is with hypergraphs, and then hypergraphs on top of those hypergraphs, and hypergraphs on top of those. It's sort of, in a way, quite natural. There's little else you could do. And it turns out that it connects to high category theory in a fascinating way. And high category theory is in a lot of churn and rapid development. So I've become interested in category theory. I didn't expect to be, but here we are. But also
the idea. I see.
Yeah.
Yeah. All right. Sounds good. Should we open up the floor one more time for any last questions from the audience? All right. Well, I think this is a good place to end. Thanks again so much for preparing this talk for us, and hope we hear more about this in the future, Tali. This is really great. I'll end the recording here.
Brendan, thank you.